In this video, we're going to be talking about scatter plots and correlation. So first, we're going to explain what positive, negative, and no correlation are in regards to a collection of ordered pairs. And it's how the x's and y's relate to each other. So we're going to kind of sketch examples as we talk about that relationship. So the first type is when x increases and y increases. And that's going to be a positive correlation. And here we can see an example of that. We have all of these points that are increasing. So as x is getting bigger, y is getting bigger, and they look like they're kind of going up in a positive sloping trend. We also have, as x increases, y decreases. And this is going to create a negative correlation. Notice in this correlation that our dots are kind of all in a general area where they're going down, like it was a negative slope or a negative line. And we also have no correlation, and that's when as x increases, y can go up or it can go down. It kind of doesn't really matter. And as you can see, the dots are kind of just like all over the place. It's like a madhouse. Let's explain what it means to fit a line to the data. When you're fitting a line to the data, you draw a line so that it best fits the data. So by trying to get some of the points on each side of the line, and it goes through as many points as possible. And this line that you create, it's a linear line, so it's going to be straight. Let's talk a little bit more about that. So after finding a model, you can measure how well the model fits the data by comparing the actual values with the values given by the model. So kind of looking at this table, right? So we're saying that the actual points were these things right here. And that our model or the equation or our line gave us these ones. So we want to know, like, how close are they? Well, the sum of squares of the differences between the actual values and the model values, we call that the sum of the squared differences. And the model that has the least sum is called the least squares regression line for the data. So for the model that we have here, the sum of the squared differences is 0.23. And the least squares regression line for the data is p equals 2.39t plus 285.2. Its sum of squared difference is 0.14. So how does that help us? What does that mean? Let's kind of talk to us about this correlation coefficient, meaning how close does our model fit the actual data? So the correlation coefficient is a value that tells you how accurate your model is to the data. And the closer that value is to either a 1 or a -1, the more accurate your model is. So something that's a 0.5 is going to be way less accurate than something that's at a 0.78. That would be more accurate. But a 0.99 would trump both of those. Let's do an example so we can kind of see how this all gets pieced together. All right, so the population P in millions of the United States from 2008 through 2013 are shown in this following table that was obtained from the U.S. Census Bureau. So we first want to construct a scatter plot of the data with t equaling 8 corresponding to 2008. So what that means is this would be 8, 9, 10, 11, 12, and 13. So we're going to start off by doing that. So I'm going to I'm going to scoot this over, I'm going to pull up my calculator, and we're going to go ahead and enter in those data points. So we're going to begin by clearing out anything that we have inside, and then we're going to go to Stat, and then to Edit, and we're going to go ahead and put in our list. So I have something in here, and I need to get rid of it. So I'm going to go up to where it says L1, and then very carefully I'm going to hit the word clear, and then enter, and it will clear all my points out for me. And now I'm ready to enter in my 8, 9, 10, 11, 12, and 13. Then I can arrow over to my list 2, and that's where I'll put my Y values. So 304.1, 306.8, 309.3, 311.6, 313.9, and 316.1. Now that we have that in, we're ready to create our scatter plot. So we're going to go to second y equals, that'll open up our stat plot, and we're going to turn it on. So we're going to hit enter, and then hit enter on our on, and now it's going to be turned on. When we hit graph, depending on what your window was, this might not look right. So we're going to go ahead and we're going to modify our window. So we're going to have our x go from 0 to 13, although really we just kind of need it to go from 8, but we can do it from 0. So from 0 to 13, and let's count by ones. And for our y's, we can go from 0, or that'd be really far. Our smallest value is 304, so let's go from 300. And let's change our 0 on the x minimum to an 8. So we'll change that to an 8, or maybe even a 5, something just smaller. We'll change it to a 5. All right, and then our y maximum, our biggest value is 316, so we can make that a 320. And let's count by 4s. And now when we graph that, we're going to see a much different line here, right? A much different line. In fact, let's change our window to go to 15 instead of 13. There we go. So we can actually get a better picture. And so let's go ahead and let's sketch what our scatter plot looks like. Now don't forget to put in the break spots right here, showing that we didn't start at 0 because we started at 8, right? And then here we started at 300. And we're just doing a sketch. And so now we have a sketch of our scatter plot. And it wants us to describe this type of correlation. Well, as x is increasing, so is our y. So this tells us that we're looking at a positive correlation. Because as the number of years increases, so does the population. Next, it's asking us to use the regression feature on the graphing utility to find a linear model for our data. So we're going to need our calculator again. And we're going to use our stat again. So we're going to go to stat, arrow over to calculate, and we're going to calculate our regression line 8. So linear regression, where we have, number 4, our ax plus b. That's like mx plus b, right? So option number 4. And then we're going to use our first two lists, and we're going to ask it to calculate, and it's going to give us our m and our b. Now what you're going to notice, though, is it didn't give us our R value, our correlation coefficient, which we're going to end up needing. So let's go ahead and let's write down what we have, and then we'll go back and learn how to turn on our correlation coefficient. And so now we have our regression model, our linear model for this data. So now, using our graphing utility, it wants us to plot that model, and in the same window. So we're going to go to our y equals, we're going to put in 2.36x plus 285.44, and we're going to go ahead and we're going to hit graph. And we're going to see our line go through the points, and it does a pretty good job of matching up. So we want to know, is the model a good fit? What do you think? And I think it is, because it went through all of the points, and the space on the top seems to be equal to the space on the bottom. But how can we figure that out using our correlation coefficient? So we're going to go ahead and we're going to turn that on. So we're going to go to mode, and we're going to arrow down to stat diagnostics, and we're going to turn it on. Then we're going to go back to stat, over to calculate, and go back down to our linear regression model and hit enter. And this time when we're done, we're going to see an R value appear. Check that out, 0.999. That is really close to perfect, really close to the number 1. So we know that this is a great model. So now we're going to use this model to predict the population in 2020. So if we're predicting that, and the 2020 is our time, we're going to go ahead and plug 20 into our equation to get an answer. Now the reason we're going to use x equals 20 is that, remember back up when we were given our data, it said that 2008 was the value 8, which means that 2020 would be the value 20. So we're going to go ahead and we're going to plug that into our model. So y equals 2.36 times 20 plus 285.44. And we can plug that into our calculator. So we're going to plug in 2.36 times 20. We're going to add the 285.44, and that's going to tell us that we should have 332.64 million people. So let's go ahead and write that down. And it's asking us, is that reasonable? And it's a reasonable answer because for the US, that many people would not overburden our land. And so we've also just constructed, using our graphing utility, a scatter plot, a linear regression model, and compared that model with our correlation coefficient to see if it was a good model, and then used our model to predict an answer.